Listo, profesor.
Bienvenidos al seminario de hoy de la red LAFMAT, la red latinoamericana de física de la materia condensada y ciencia de materiales. LAFMAT es una comunidad que tiene como objetivo divulgar los avances de vanguardia de los investigadores latinoamericanos y facilitar la interacción entre investigadores latinoamericanos y destacados investigadores de todo el mundo. La red está integrada por investigadores de la Universidad Mayor de San Marcos en Perú, la Universidad Federal de Pernambuco en Brasil, la Universidad Rural de Río de Janeiro también en Brasil, la Universidad Fluminense de Río de Janeiro, la Universidad Nacional de Colombia, el CIMBESTAF de México, la Universidad de San Sebastián en Puerto Montt, Chile, la Universidad del Zulia en Venezuela, el Centro Atómico de Bariloche en Argentina, la Universidad de Córdoba también en Argentina y varias universidades más de Latinoamérica. En el día de hoy es una alegría presentarles al doctor Dibya Prakash Rai. El profesor Rai es profesor asociado en el Departamento de Física de la Universidad de Mizoram en India. Obtuvo su doctorado en la Universidad de Mizoram en el 2013 y realizó estudios postdoctorales en el Centro de Investigación en Ciencias Computacionales en Pekín, China, desde el año 2013-2014 y en Jülich, Alemania, desde el año 2023 al 2024. Ha publicado más de 250 artículos científicos y ha completado 5 importantes proyectos de investigación. Actualmente ha sido nombrado editor invitado de la revista The International Journal of Energy Research. Además, ha publicado 2 libros como editor: Advanced Materials and Nanosystem, Theory and Experiment, con la editorial Betan Science. El título de la charla de hoy es Pressure Dependent Non-Relativistic Spin Splitting in Altermagnets. Welcome, Professor Rai. It's a real pleasure to have you here and give you the opportunity to give this talk.
Thank you, Professor Alexander, for a nice introduction. I would like to say good evening to all my friends from Asia, and good morning to all the people, the scientists, and the audience at the South America and American continent. I would like to thank Professor Luis for inviting me. We became friends at Vietnam when we were visiting there. So in a very short span of time, we became very close, and and throughout our WhatsApp, Facebook, and everywhere we start chatting, and finally we'll end up to this kind of programs. And once again, thank you for the invitations, and I hope we'll have a nice interactions. So oh, sorry, I just make a mistake in my title, this ultramagnetic materials, but yeah, the idea is the same. So my name is Dr. DP Rai. My name is very long, so many people cannot say correctly, so I write shortly, DP Rai. So I'm an associate professor in the Department of Physics, Mizoram University, Aizawl, India. So today I'm going to talk about the spin splitting in the FeSb2 materials, which is basically an altermagnetic materials, which has already been proven by theory and experiment as well. So why ultramagnetic materials? Oh, so by the way, Alexander, can you tell me how much time I have?
As much as you want, 40, 50 minutes, depends on you.
Okay, so thank you. So why I'm interested in this kind of materials is for my research topic is because I read one newspapers and that is the headlines was the textbook update in a schools and the college level in India, and it was written something like ultramagnetism emerges as a new class of magnetic order. Whether this topic should be included in the school level or the college level syllabus or not. Then I started, knowing more about these ultramagnetic materials, and then I found this is a new magnetic order in between the ferromagnet and the antiferromagnets. So that is how I shift my interest to this kind of materials. So in introduction, why altermagnetic materials? Why magnetic materials in general? Okay, so over the last 2 decades, spintronics has a lot of promises due to its low energy consumption. People believe that the devices which is based on the spin technology will consume less power than the charge technology, and it will offer faster data transfer, and the storage system will be high. So there will be a lot of storage systems. So traditionally, ferromagnet materials are believed to be the best candidates for spintronics technology or spintronic applications, where the spin of the electrons are spin degrees of freedom of the electrons are manipulated to transport the charge or store the charge, all these things. And why ferromagnetic is believed to be the best materials for spintronics is due to their spin polarization at the Fermi level and the finite value of total magnetic moments. Okay, so that was the reason that people believe ferromagnets can be a better candidate for spintronic devices. But later on, when it comes to the practice, it has some deficiencies. So the deficiency is like the presence of stray field. Because of the stray fields, it hampers the performance of the device. Okay, then it hampers the performance of the device because there is a damping when you flip the spin in ferromagnetic materials. And people again shift their interest towards antiferromagnets. So why antiferromagnets? Because the spin flip is very fast, and spin dynamics is around in terahertz scale. It is very fast. So there will be no damping, and it is free from the stray field type of deficiency. But another important part missing in the antiferromagnetic materials is lack of spin polarization at the Fermi levels. So there arise always the Kramer's degeneracy, which makes them unfavorable for the spintronics, because according to the spintronics technology, the spin polarization is the key features out here, but that has been missing in antiferromagnetic materials. And now another materials has been proposed in 2022, and the prototype material was RuO2. This material has been named antiferromagnetic materials. So let us see what are its properties, why it is different from ferromagnets and antiferromagnets. So ultramagnet represents a new class of magnetic ordering. This combines the merit of ferromagnets as well as antiferromagnets. So it exhibits spin splitting bands without a net magnetic moment. So you have all the magnetic atoms are sitting antiparallelly. Okay, so there is an anti-parallel coupling, and the overall magnetization is zero. That means there is a compensated magnetizations. Despite of that, there is a degeneracy of the electronic band. So the degeneracy has been lifted out here even without applying any spin orbit coupling. Okay, so origin of altermagnetism lies in the symmetry allowed by breaking of time reversal symmetry. Generally, when you have antiferromagnetic materials, and if you want to have the two spin split bands, then probably we use spin orbit coupling. So when we apply the SOC, spin orbit coupling, so SOC means spin orbit coupling. Those who are from DFT and all, they will know, but from experimental people like maybe they will not know. But when we apply the spin orbit coupling, it will break the time reversal symmetry, and it will give you the two bands. The bands will be split. So the prototype materials is RuO2, and this has already been proposed in 2022 by Sumakel and his group. And how does the electronic bands or the spin bands looks like for the three types of compound: ferromagnetic materials, antiferromagnetic materials, and the your what do you call uh, 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 your altermagnets. So here, uh, when the bands are not spin degenerate, the time symmetry is broken in case of ferromagnets, just like in the G-men splitting or spin orbit coupling. Okay, and like inversion symmetry is broken. This is for non-symmetric materials, that is like Rasava or the spin SOC is required. But here, none of them are applicable here, right? For in case of altermagnets. So the band splits by itself because of its symmetry. So let us discuss about like ferromagnetic materials and antiferromagnets and the altermagnets based on their the spin based on their spin symmetry and spin symmetry and breaking. So here, if you have ferromagnets, all the if you see the left hand side, you have blue dots, sublattices are there. So those are the sublattices, blue. And let us say this blue dot represents the spin up. All are spin up. And if you apply the time reversal symmetry, then the spin flip will be there. All the dots will become red. So red represent the spin down. Now, if you apply the inversion symmetry, the final state and the initial state are not the same. So we call that the time reversal symmetry has been broken. So because of the broken of the time reversal symmetry in ferromagnets, so you have the spin split. So you have the distinct spin down and spin up bands in your band structure, right? So another case is for antiferromagnets. If you go for an antiferromagnet type of materials, then you have how the uh, atoms in the sublattices are sitting. They are like in alternate positions, like blue dots, red dots, blue dot, red dots. They are in the alternate position. So I have already said that blue dot represents spin up, then you have spin down, then have you spin up and spin down. Okay, so you have basically antiferromagnetic coupling. So if you apply the time reversal symmetry and you apply the inversion symmetry, then the final position, I mean the final state and the initial state and the final state will be same. Okay, so there will be no change in the symmetry. So there is an invariant. So because of that, the time reversal symmetry is not broken, right? So the so there is an invariant in the system, then you will not find any broken symmetry. So as a result, there will be no band splitting will be there. So you cannot distinguish, you cannot get the two distinct bands, spin up and spin down bands, like in the case of ferromagnets. So here this is the case of your antiferromagnets. The spin up and spin down, you cannot be separate out because of the invariant in the symmetry. So here now another type of materials is altermagnets. So altermagnet, you will see how the atoms are sitting. So you see that the blue red atoms on the left hand side, blue, let's say spin up and the red is spin down. But if you see the environment around them, it is different. Okay, you will see in the blue, you will see the diamond which is facing up, and if you see the diamond surrounding the red dots, it is uh, like on the horizontal line. Okay, so it is on the horizontal line, and this axis, you just say that on the red axis it is horizontal, and for the blue axis it is the vertical, right? So when you apply the time reversal symmetry, spin up will become spin down and spin down will become spin up. So in this case, if you apply the inversion symmetry, then the two states are not the same. So here, because of the anisotropy, I would say the anisotropy of the local environment, the like your time reversal symmetry has been broken here. So because of that, you will find the spin splitting in altermagnet. So this is the picture of your ferromagnets, anti-ferromagnets, and the altermagnets. Okay, so here A, B, and C represent the ferromagnet, anti-ferromagnet, and the altermagnets. So A here you will see the spin density. So this is the spin density. So all the spins are oriented in one directions. Here the spins are like almost symmetric. You will see there will be no any the spin almost symmetric in the antiferromagnet spin density. Here you will see the spin density is like a dumbbell shape, and they have a different directions. So because of that, there is an anisotropy in the in their lattice, okay, or the local environment. So as a result of that, you will see the time reversal symmetry has been broken. Okay, so now if you see the band splitting in the ferromagnets, you will see the distinct splitting of the bands. In antiferromagnets, there will be no splitting of the bands. The two bands are degenerated. But here you will see the bands are splitted, but they're in a different way. Okay, in a like what to say, in a symmetric. They are symmetric, but in a different pattern here. So the difference is like in ferromagnets, band splitting is there, but here in antiferromagnet, band splitting is there, but they are like symmetric. Okay, so symmetric splitting is there. So this is the difference. So we can differentiate from here. Yeah, this is I already explained like how the time reversal symmetry has been broken in altermagnets. So you know that ferromagnets, all the the moments are oriented in one direction. In collinear antiferromagnets, they are anti-parallel to each others, and non-collinear antiferromagnets, the spin are random. Okay, and this is the starting point, and this is after the time reversal symmetry. And if you inverse if you apply the inverse symmetry, they are not the same. Final state and the initial state will not be the same. So there is an anisotropy. So this anisotropy plays a crucial role in breaking the time reversal symmetry in case of your altermagnets. So here we can calculate the splitting, the value of the splitting. That's very simple. Like you can just take the difference of these two. You will get the value of the splitting around the Fermi level, right? So the historical background of altermagnets starts in 2022. It was first coined altermagnet in 2022, and the prototype materials was RuO2, and this was discovered by Semakel and their groups in Czech and in collaboration with some German physicists. And there are a lot of work has been done, and from DFT and symmetry-based conformations. And in 2025, experimental validations and device applications are also published in 2024 and 2025. So distinctive features of altermagnets are there is no net magnetizations. Despite of that, there is a band splittings. Okay, so the time reversal symmetry has been broken without the spin orbit coupling. But in the case of antiferromagnet, time reversal symmetry has been broken because of the spin orbit coupling, and it will have finite Berry curvatures like features, which almost similar to the ferromagnetic materials. So how will we select the antiferromagnet material? Altermagnet materials. So there are some criteria to select the altermagnet materials. The first criteria is in the unit cell there has to be a even number of magnetic atoms in unit cell. The first criteria is there has to be, because technically they will remain anti-parallel to each other, and they will give the compensated magnetization. So that is one criteria. So the two atoms, or the two magnetic atoms should not be related by inversion symmetry. Okay, so so that is another criteria. So another criteria is presence of inequivalent local environment surrounding each opposite aligned spin sublattices. So they should have some kind of anisotropy in their local environment. So that is another criteria. And the So last criteria is opposite spin sublattices are connected by rotation in spin and real space combined with the translation and inversion symmetry or the Clyde symmetry. So that I will explain later, the last part. And there are different types of altermagnets, D-wave type altermagnets, G-wave type altermagnets, and I-wave type altermagnets. So you will see based on their Fermi surveys, we can distinguish whether it is a G, D, or the I type. And D-wave type, you will see the example of RuO2, FeSb2, CrSb2, all this comes under the D type altermagnets. And G type are CrSb, which is having mostly rhombohedral or the hexagonal type of structures, they will have G type. Then I type will have 12 lobed spin polarization in the K space, and this is CRI3 to H FeB3. So these are the examples of the I type of these things. So I have worked mostly on the D wave type of altermagnets, not on the G and I wave type. Experimentally, altermagnets has been confirmed in many papers, which has been reported. But this is the papers that has been, I found, and how they have confirmed is by technique called RPS. So from the RPS, what they have detected is they have detected the spin splitting. I think experimentally there are no other techniques other than RPES to detect to confirm the your altermagnet behavior, because only from the RPS you can get the picture or the profile of the band splitting. So there are many materials so far which has been confirmed altermagnets, and CrSb2, MNTE2, all these materials has been experimentally proven using the RPES technique. And except RuO2, in RuO2 they could not get the splitting, but theoretically RuO2 is the prototype materials, and it has already been, there is a lot of controversy in RuO2 despite it is being the prototype material. Now I will come to my work. What I'm doing is like I'm doing a density functional theory to get the band structures and density of states, all these things using the density functional theory. So density functional theory is a quantum mechanical tool to determine the ground state properties of many electron system using the electron density rho rather than the many body wave functions. So in quantum formulations, the interacting electron system, there are so many interacting system. In reality, there are so many atoms inside the crystals, and there are so many electrons. So they are interacting with each other, or they are communicating with each other. To tackle them, all of the things, I mean, all their interactions is very, very difficult. So there is an approximations. They made the approximation. So instead of taking interacting electronic systems, let us consider it's a non-interacting electron system. If you approximate in that way, then our system will become more, our problem will become more simple, just like in the Hartree-Fock case. In the Hartree-Fock case, all the interacting systems are now, reduced to the non-interacting system, and which gives you the electron density, just like in the Hartree-Fock approach. Okay, so by taking that approach, the Kohn-Sum equation has been formed, and this Kohn-Sum equation is solved self-consistently. Okay, self-consistently to get the ground state properties. And later on, the last term in equation 4, Vxc, has been added on. Why it has been added on is because when we try to make the complex problem to a simple problems, what we have assumed is that, like, in reality it is the interacting system, but how we proceed our problem is like it is considering as a non-interacting systems. So the quantum mechanical interactions part has been missing there. So that missing part has been compensated by adding this Vxc. Okay, this is called the Xn correlation function. Okay, then we solve the self-consistent calculations. We will get the electron density, and this electron density will give you the new type of potential. So every time it will give you the new type of potential. So according to the Hohenberg and Kohn theorem, second theorem, it says that this rho, that is the electron density and the potential, are one-to-one correlation. So if you develop a rho, then you can develop potential. So that way we solve, and we can get, finally we get the ground state electron density, which is unique to that particular system. And then by taking that unique electron density, we will get the other observable properties. So that is how the density functional theory works, and from there we can extract all other physical properties like band, DOS, forces, etc., etc. And now altermagnetic property. So altermagnetic property arises because of what? So altermagnetic properties because of the multipolar magnetisms. Okay, so if you see, the magnetization density can be expanded in multipoles, right? So it started from the monopole, dipole, then quadrupole, octopole, and all. In reality, so this is your expansion of the magnetization density. In reality, monopole does not exist, right? And you have a dipole, and this dipole contributions will be zero, right? Dipole contribution is zero because they are anti-parallel to each other. So because of that, it will become zero. And the second part is, third part is your this one, magnetic quadrupole. And magnetic quadrupole also does not contribute because of the symmetry of the system, because our system is symmetry. So because of the crystal symmetry, so it will give you basically the net magnetization will be zero. And the last the another part is the octopole moment. In octopole moment, this is very small in the real case, but here it still exists. So it is not zero. Why it is not zero is because of the like orbital projection. So orbital have a lot of projections. So because of that, you will have the octopole magnetic octopole in case of altermagnet. So that way we can simplify the things, or we can explain the things. So this is a little bit of mathematics for how the electron how the magnetization density is expanded, right? So the magnetic interaction energy, EINT, is given by this one, integration of mu r HR and T3R. So what is HR here? HR is the non-uniform magnetization, and UR is the local magnetic moment density. And this has been the sum of, the product of these two will give you the interaction energy, magnetic energy. Okay, so that is the magnetic interaction energy. So now this HR, which is the non-uniform magnetizations, it is in the expanded form. Okay, so let us expand this in Taylor series. So you will see like this kind of things out here, and basically you will, this is H0, then this is the 0th order, this is the first order, this is the second order, and this is the third order. So 0th order does not exist because monopole does not exist, that we know. Then you have the first order, that is because of the dipole, and this dipole is also cancelled. This will give zero. I have already explained these things. And you have this term will contribute to your quadrupole, and quadrupole is also zero because of the crystal symmetry. We have a symmetry crystal. Our system is very, very symmetric. So because of that, so quadrupole doesn't play any role. So the last existing term is this one, that is the third order term, that will give you the octopolar moment. So octopolar moment comes because of the orbital projections. Okay, so orbital projection. So this is the only existing term. So that is responsible for breaking the time reversal symmetry in altermagnets. So this I have already explained, I think. So no, not required. 0th order, first order, and you have second order and the third order. 0th order is for monopole, and the first order is for dipole, and the second order is for your quadrupole, and the third order is for your octopole. So, so this I have already explained. A monopole vanishes because in reality you don't find any monopole. Dipole, they vanish because they are anti-parallel, so they cancel each other. And the quadrupole also vanishes because of the crystal symmetry. And octopole, it vanishes because you have a spin orientation alternate in such a way that it creates anisotropy in the local spin patterns. So I have already says that there is a like anisotropy in the local spin pattern. So that is responsible for breaking your time reversal symmetry. Okay. So as we know that ferromagnets also have a spin splitting, and the ultramagnet also have a spin splitting, and ultramagnets have the characteristic of ferromagnets, and at the same time ultramagnets also have the characteristic of your antiferromagnets. What is the characteristic that ferromagnetic characteristic that is present in the ultramagnet is the band splitting, and what is the characteristic of antiferromagnet that is present in the ultramagnet is the compensated magnetizations. And just like in the case of ferromagnets, uh, ultramagnets also have finite value of Berry curvature, and we can calculate these Berry curvatures, and from the Berry curvature integration of the Berry curvature multiplied by your Fermi functions will give you the anomalous Hall conductivity. Okay, that is according to your Kubos formula. So this is the your Berry curvature, and you have integrated the Berry curvature multiplied by the Fermi functions, you will get the anomalous Hall conductivity that is based on your Cooper's formula. And Berry curvature is basically, it is like a magnetic field in your K space. So it acts like that. So because of that, you will get this AHC, anomalous Hall conductivity. Now, our results, this is the structures of RuO2. This is prototype structures. And you will see here, and Ru atoms are like at the corners, and also the Ru atoms are sitting at the center. But if you see how the oxygen atoms are, like connected with the Ru atoms at the corner, and the Ru atom at the center is different. So the diamond at this corner is different from the diamond at the like center. So there is an anisotropy. Now if you see, if I have already said that there is this thing anisotropy. So you see that one, if you flip by 90 degree, then you will see this one. Okay, you will land up to if you come diagonally in this diagonal directions, if you flip by 90 degree, so there will be a C2 symmetry. So that is one of the criteria that I said, like I wanted to explain this later. So the first at the corner atom, suppose this corner atom, if you translate in the diagonal directions, at the same time if you flip by 90 degree, then there will be an anisotropy. Okay, so there's an anisotropy. So that is one criteria for selecting the ultramagnetic materials. So there is a fourfold symmetry. Now, what we did was like FeSb2 under pressure. FeSb2 has already been reported ferromagnet, antiferromagnets, and it has also they reported it is ultramagnets. It was already published, but what was missing in that paper was like they did all the calculations at the ambient conditions. Ambient conditions. So we wanted to do something different. So we applied pressure from 0 to 10 GPa, and because 0 GPa, it was already reported, so we did not report that one. So we did all the DFT calculations and all the things, and up to 10 GPa we have found there is a band splitting, but beyond 10 GPa our system is completely non-magnetic. It doesn't show any band splitting. So the ultramagnetic behavior, it preserves up to 10 GPa. So beyond 10 GPa, it does not exist. And we have found that the spin splitting, this maximum at 0, that is 0.55 electron volt. And when we go, when we increase the pressure, the spin splitting also decreases. and this is how we report. So up to 10 GPa, we have found out the spin splitting, but beyond 10 GPa, maybe 10.1 or 11, it might be there, but we did only up to 10 because this is the minimum that we could report at 10 GPa. And beyond this 10 GPa, there is no splitting. So that is our report, and we have also calculated Berry curvature of FeSb2 under pressure, and we have found the Berry curvature are finite up to 10 GPa. So when we go beyond 10 GPa, it is the magnitude of the Berry curvature is small and smaller. So our materials FeSb2 is a altermagnet materials up to 10 GPa. Beyond 10 GPa, we report that it is the non-magnetic materials. So we found out, we calculate all the transport calculations and all these things, and we found that around 100 Siemens per centimeter AHC, anomalous Hall conductivity, at around the Fermi level, which is almost equal to some of the ferromagnetic materials. So we have also extended our calculations for RuO2 thin film, and we have created the thin film for 00. This is the ultra thin film 001 directions, and we have done optimization and we have done some calculations, and we report that like our splitting is maximum for six layer, up to 6 layer, then it is decreasing. So that was what we have reported. And this is the band is splitting for our case, the 2D materials. And we have also calculated the Berry curvature, and this Berry curvature is finite. That means there is a spin splitting. So this confirms that there is a spin splitting. And we have also calculated AHC and SHC also, but SHC probably I have not reported here. So in RuO2 thin film, in experimentally up to like magnetic field up to 10 Tesla, 50 Tesla. So it was around 1000 Siemens per centimeter AHC. That has been reported in experimental papers. But in our papers, we have reported only 250 Siemens per seconds. Centimeter for the bulk. And for our case, in the layer materials, our result is around 300, 600, 1000, and 1500. That is very close to these experimental reported results. So significance and applications of these materials. Automagnetism is promising materials. People believe that this is the new potential candidate for spintronic applications because of its merit properties that has been taken from ferromagnets and the antiferromagnet materials. So and the breeze gap between ferromagnet and antiferromagnet. So this will give you a new kind of understanding how we will understand the new type of magnetic materials that will breeze the ferromagnets and antiferromagnetic, the concept of the antiferromagnet and the ferromagnetic materials. So possible application in CMOS technology, memory devices, quantum computing, all these things. And in conclusions, I would say from our calculations, our results, we report that FeSb2 is an altermagnet materials under pressure up to 10 GPa. Beyond 10 GPa, it is a non-magnetic materials. And while increasing your applied pressure, the splitting has been reduced from 0.55 electron volt to 0.1 volts. And our AHC for the FeSb2 is around 100 Siemens per seconds at the Fermi level at 0 GPa. So at 0 GPa, we have found out the maximum AHC. So that is what we have found out in our results. So this paper we have already submitted to Physical Review B. Now we are defending a second time. So I hope this will publish very soon. So these are my references. And these are the people in my group. I have around 9 students working with me. One is postdoc, and all other students are the PhD scholars. They are very hardworking. They are doing different types of works, not only on the magnetic materials. Some are doing on the energy materials. Some are working on the battery and all so on. And these are my collaborators, Dr. M.P. Gimire from Nepal, Professor Darwin from Philippines, Dr. Shrestha from US, Professor Tin from CTU, Vietnam, and Dr. Sami from Algeria. Professor Sami Lunis is from Germany. In fact, he's my postdoc supervisor. And this is the day and this is the time that we met with Professor Lewis, and we discuss all the academic related things and research related things. And we have, from that time only, we plan like for this kind of program. So thank you for your invitations and thank you for your patience.
Thank you, Professor Rai, for your presentation. Very nice work. We now welcome questions on the presentation. We invite Professor Tien Nguyen from Canto University in Vietnam. Professor, do you have any questions?
Yeah. Can you hear me?
Oh, hi, Professor Tin. How are you?
Yeah.
Nice to see you.
Yeah. First on, I would like to thank all of you at come web seminar today. I would like to. I think your presentation is very nice for me. It is the new state management in new state. I have two questions for you. I think you resign. You explain the polarization magnetic in the 3 dimension for the part 1, part 2, and part 3. I want to know, are there the difference between the 3 dimension and 2 dimension for the plan polarization? The second one, you can rumor spin chamber in your new new state, new material, new mechanism. You talk about that. Thank you.
Okay, the first question is like the difference between the bulk and the thin film, right?
Yeah, 3 dimension and
yeah.
2 dimension. Yeah.
Yeah, generally we didn't find any difference there. Obviously, in terms of magnitude, yeah, it is there, because in bulk we are getting higher splitting, and when we go for the 2D, like ultra 2D scale, the splitting has been reduced. But in both the cases, our splitting is in plane splitting, so there is no difference. But in terms of magnitude, yes, it is there. What was the second question?
Second question, you can more detail about the spin chamber by the new state, new magnetic state. I know that it's the magnetic and the paramagnetic, but if you use the spintonic, you can estimate the IV characteristic with the spin magnetic coupling. I don't know the state which you can plan more spin chamber.
Yeah, that's a good question, but I'm doing only the basic type of calculations. You're generally talking about the device, right? Like transistors and all these things, like how the spin transfer or those kind of things are done. So I have not looked into that part so far. I'm just basic part. I'm concentrating on the basic concept and all these things. So maybe it can be done like we can make the device by like the spin transfer, like how you inject the spin into the insulator or the semiconductors and all these things. So that might be possible, but so far I have not done that kind of calculations.
Yeah. Thank you.
Thank you.
Thank you, Professor. We now invite Professor Diem Bo from Kanto University, Vietnam. Professor, do you have questions?
Apparently, Dian has problem with his microphone. He's typing.
Okay. We now then invite Professor Augusto Moreira from University Federal de Pernambuco. Professor Augusto, do you have any question?
You hear me? It's okay?
Yeah.
Yeah.
It's fine.
Okay. Nice presentation. And I have two
Thank
questions. How do you implement the DFT code? It's a kind of software or a self-made program? This is the first question. And the second is this kind of symmetries you can find in organic systems like doped graphene or something like this.
Okay. Software, like we have used multiple softwares here, so that's why I have not mentioned here. And we have used VAS also, and we have used quantum espresso also. In some calculations, we have used crystals also. So, and second question is, yeah, there are like many organic organic molecules based like altermagnets has also been reported, but I have no idea about organic altermagnets. I have not worked on that. Maybe the theory is the same, the basic principle is the same. So yeah.
Okay, nice. Gracias.
Gracias.
Thank you. We now invite Leandro Tosi from Centro Atómico de Bariloche. Leandro, do you have any question?
Hello.
Hi, Dr. Tosi.
Yes. Yes, so I have a question about I found these altermagnets very interesting. And my question was if beyond the editing is easy, there are some other stuff that would be interesting to some skins of experimentally materials with interesting properties, like for application.
I cannot hear you. If anybody hear his voice clearly, you can translate to me. I cannot hear.
Leandro, can you please repeat your question, because probably your connection is not good. Okay, I think Leandro is having problems. Now we invite Professor Isaías Oliveira from Universidade Federal de Rio de Janeiro. Professor Isaías, do you have any question?
maybe they can type if some problem with their microphones.
Okay.
Okay now?
Yes, please.
Okay, so sorry. I mean, connection here is very bad. So I really want to I really said that I appreciated a lot your explanation and the pedagogy, because I have been hearing a lot of these talks about the altermagnets and this new state of magnetism, and I found this very clear, at least to understand what is there to look for.
Oh,
so thanks a lot for clarifying this. It was very nice.
That's
the
best compliment.
I mean, I'm okay. I'm an experimentalist, and I normally, I mean, theoreticians, they come with saying, this is very interesting, this material. I have seen a spin splitting of like a very small micro EV, and then it's like almost impossible to see and almost impossible to fabricate. So my question is, like, beyond like the DFT, looking for the spin splitting and so on, is there anything else to look for in these altermagnets that could be interesting or a nice property for experiments, like would be useful for some other application?
Yeah.
Sorry.
Okay. And that I have already explained, like experimentally, if you go, like it goes up to antiferromagnets, right? So if you want to go check beyond antiferromagnetic materials, I mean the antiferromagnetic properties, you have to go for RPS. RPS is the only, I think, confirm like technique that gives you whether your materials is antiferromagnets or altermagnets.
Yeah, I mean,
because basically you have to check the spin splitting, right? So if the materials is antiferromagnets, you cannot get the spin splitting. Only in case of your altermagnets you will get the spin splitting, and this spin splitting can be traced only from the RPAs.
Okay, perfect. Yeah. Yes, I mean, I understand that. No, my issue was like, if there was something, other property to calculate that would point to a material that is interesting for application, not only checking that it's an altermagnet, but using it for something. That was the question.
Yeah, but I have no idea, like if you want to see some interesting properties, right? Some unusual behaviors, or something, some anomaly in the results, that kind of things you wanted to know, right?
So in principle, it will just behave like an antiferromagnet.
Yeah, it is. Yeah, it is an antiferromagnet because you have a compensated magnetizations. So unless and until you will do RPS, or like you can go for some kind of transport calculations like AHC or SHC, altermagnet cannot be confirmed.
Well, okay. Well, thanks a lot, and really appreciate all the explanations. Thanks a lot.
Well, thank you very much.
Okay, thank you. Do we have any other questions? Luis?
No, I don't have questions, sir.
Okay, thank you. And Melby and Jimena, are there questions from the social networks?
Good morning, Professor Alexander. No, we don't have any questions from our social networks. Thank you.
Thank you.
Okay, thank you. And now, please, can you stop sharing the screen, Professor Rai? We now invite all the persons present to turn on the camera. Professor Rai, do you have any last question or last words to say to the Latin American network?
Yeah, I am very pleased for these invitations, and I got a lot of interactions. I came to know many professors, many good scientists here, and that is what like I was always looking for. And it's a great meetings, I would say. And I would like to thank all the professors, especially my friend Professor Luis, and we became very close friends in a very short time. I think we had one dinner, so I think after one dinner we were very close now. So probably we will meet him again in Vietnam this by the end of this year in December or January. So it's nice. And one more thing I got, one benefit is like I came to know Professor Augusto, who is a Brazilian professors. I was looking for some like partners from Brazil, China, or South Africa. So my motive has been, I think, successfully, achieved. So I would like to thanks all for for your patience. And some of you, I came to know that when I check the timing, you people are wake up very early. In India, like the working time starts at 10. So here some people are attending this, like meetings at 6 a.m. or like 7 a.m. So that's too early for us. But here it is evening, no problem for us. Thank you all.
Right.
Yep.
Right. Here I am in China now. Here is
Oh, okay.
10 p.m. 10 p.m.
Okay, okay, yeah. China is, I think, 2 hours before us. Okay, thank you. That's all. So I hope we will continue this kind of programs in future also. So probably I will give more talks on my new research also. So I would love to hear all the things. And actually I wanted to attend all the talks and all because Professor Luis keep on posting in the Facebook and all, but it is mostly in Spanish. So I'm I'm non-speaker of Spanish, so that's why I could not attend. So
Okay.
otherwise, I love. Thank you very much.
Sorry for that. Well, thank you, everybody. We appreciate again your presentation, Dr. Rai. Thank you very much. And well, now we say goodbye to Professor Rai.
Okay, gracias. Thank you.
Goodbye.
Bye.
Microphone, please.
Bye, everyone.
Bye.
Bye.